Hello everybody and welcome to the last session of trigonometry or chapter 4 of advanced functions. Today our lesson is going to be a little bit long, but it's also probably going to be the most exciting part of trigonometry, at least for me. So today we're going to learn how to prove trigonometric identities. You've done this in grade 11, but in grade 12 we have a little bit of a step up with the amount of content we need to know to prove these identities. So first we're going to talk about what trigonometric identities actually are. Then I'm going to show you all the needed formulas and other identities you need for this chapter. And I'm going to add a mini lesson on double angle formulas, which you might need, because personally my school tested us on them as well, even though they weren't part of the textbook. Lastly, I will be providing you with various strategies for proving trigonometric identities. So up first, let's talk about what trigonometric identities actually are. Well, a trigonometric identity is an equation with trigonometric expressions that is true for all angles in the domain of the expressions on both sides. So essentially what that long-winded description is telling us is that you'll be given an equation, and then you have to prove that the left side of the equation is going to equal to the right side of the equation for all possible values. So in this chapter, you might be asked to prove that something is an identity, or prove that an equation you're given is not actually an identity. So to prove that an equation is an identity, it's quite simple. All you have to do is treat both sides of the equation independently, and then transform those expressions on one side into the exact form of the equation on the other. So again, we're trying to make them equal. If both sides are the same exact thing, then they must equal to each other no matter what angle we use. With that being the case, to prove that something is not an identity, you could determine a counterexample. A counterexample might seem like finding another equation that this equation should equal to, but actually all that means is you need to provide a value that does not satisfy your equation or your given equation. So for example, we have the following equation given to us. Sine of a minus b is equal to sine a minus sine b. We know that this is false from previous chapter. So from here, we need to say and prove that it is indeed false. Since we know how to derive sine of a minus b, we could go through the long-winded derivation of that equation and then show that that doesn't equal to sine a minus sine of b. However, we could also simply just substitute two values in for a and b. So I chose that a is equals to pi over 4 and that b is equals to pi over 6. So from here, I just plugged it into the first part of the equation, or the left side, and I got that equals to sine over pi over 12, which then, if you just click that into your calculator, you'd get approximately 0.2588. Doing that exact same thing on the other side, where we plug in a and b, we actually find out that that side is equals to 0.2071. Since those two values don't equal, we have proven that for this particular point, the equation is not true. And since for a point, the equation is not true, therefore it cannot be an identity. As I said before, it has to be true for all possible values of the domain. So that is the process for figuring something is not an identity. However, if you actually need to prove something is an identity, you will have to know various formulas and even other identities. All of these we have already discussed this chapter, and some of them you should remember from last year. Over here, I've written out a nice list of what those equations actually are. So you need to essentially memorize all of these if you want to succeed. I know this list might seem a little bit extensive, like what do we have? 6, 6, 9, like 15, 16 different equations. And we also have the double angle formulas. But the more you work with them, the easier they become to remember. Again, this one should be engraved in your head already. Also, should these three, as they're the reciprocals of the primary trigonometric ratios. These ones are new, but as I told you in last class, they're quite easy to remember, and for that reason, again, you shouldn't have a big problem with them. So, with that being the case, you might also need your double angle formulas, which, as I said before, was a bonus unit or extensive content that we received in our school. So, what are double angle formulas? Well, double angle formulas show how the trigonometric ratios for a double angle, which is 2 theta or 2x, whatever your variable may be or your angle may be, are related to the trigonometric ratios for the original angle of theta. So all we're telling you here is that we had some angle theta, and then we were like, what if we multiply it by 2? How would that change the outcome? What would our relationship be to the original angle? So the way you find this out is you could use the compound angle formulas. You might remember that our compound angle formulas have the addition part of them, right? So you have an angle of A plus angle of B. So if both of those angles were A, that would be essentially the same as doubling it. And from that point on, you could derive all of your double angle formulas. I'll be showing you this in a couple of moments. Okay, so let's get started. At first, let's deal with sine of 2x. So this is our double angle that we have to deal with. How can we write this out? Well, we could write this as sine of x plus x, right? From here, we could actually apply our compound angle formula. So let's write down what that formula actually is. So it is sine of A plus B is equals to sine of A cos of B plus cos of A sine of B. Now let's plug in the values. So what we get is sine of x plus x is equals to sine of x cos of x plus cos of x sine of x. As you can see, these are the exact same arguments, right? So we have sine x and sine x, cos x and cos x, which means we could just add them together, which would mean we have a 2 in the front, and then sine of x, cos of x. So we found our first double angle formula, which is sine of 2x is equals to 2 sine x cos x. Now we should do our cosine double angle. So again, let's do the same strategy. Cosine of 2x is the same as or equals to cos of x plus x. Now I'm just going to write down what cos of A plus B is equals to. Cos of A plus B is equals to cos A cos of B minus sine of A sine of B. Now that we have this, we can once again substitute those values in. So cos of x plus x is equals to cos of x minus sine of x sine of x, which when we actually realize that we're multiplying the same variables together, we have a squared forming. So we get cos squared of x minus 2 sine squared of x. This is the correct way to write that, by the way. Like, you wouldn't write sine x squared because that simplifies. That is signifying that the x got squared instead of the full expression being squared. So I think you could write it like this, but again, that's not the proper convention. So that's the way we actually write it in mathematics. From here, we can actually derive other variations of what cos 2 of x equals to. But at first, let's write down our first found formula for the double angle of cos. So cos 2 of x is equals to cos squared x minus sine squared x. So from here, let's keep going. What do we remember about cos squared x and sine squared x? Well, we have a very nice identity that we learned last year, right? And that identity is that sine squared of x plus cos squared of x is equals to 1. So from here, what we could write is that sine squared of x, for example, is equals to 1 minus cos squared of x. Now, let's substitute this value into our found equation. So if we were to substitute sine squared of x into here, we would get cos squared of x is equals to cos squared x minus 1 minus cos squared of x. This would equal to cos squared x minus 1 plus cos squared x. Now we could group these two together and we get 2 cos squared x minus 1. This is our second variation of the double angle formula for cos. So cos of 2x is equals to 2 cos squared x, sorry that's bad, equals minus 1. We could do that exact same thing for substituting in for cos squared of x. So again, using this, we could find out that cos squared of x is equals to 1 minus sine squared of x. Now, let's substitute that back into our first equation, and we would get cos of 2x is equals to 1 minus sine squared of x minus sine squared of x. Again, we group those two together and we get 1 minus 2 sine squared of x. That is our last variation of the cos of a double angle. So what we get is cos of 2x is equals to 1 minus 2 sine squared x. You should remember all three of these variations because again, they'll be extremely helpful for when it comes to solving trigonometric identities. Lastly, we have our tan function. Also, I'm going to extend this a little bit. There you go. So, tan of 2x. Last time, I didn't actually prove of how to derive tan of a compound angle. However, that was one of the extended questions in the textbook. So maybe if you did, you would understand it. But again, the idea there was to transform the tan function into sine x over cos x and then apply the other compound formulas you've learned. So what we learned from that, again, is that tan 2 of x is equals to tan of x plus x. And tan of two angles, so a plus b, is equals to tan of a plus tan of b over 1 minus tan a tan b. Okay, so now let's again go through the same method. We are substituting in our x plus x values, and what do we get? We get tan x plus tan x over 1 minus tan x, which we could now group or multiply the exact same variables together. And what do we get? We get 2 tan x over 1 minus 2 tan squared x. Therefore, I'll write it over here. Therefore, tan of 2x is equals to 2 tan x over 1 minus tan squared x. as you could see, all these derivations are actually really simple. We're just plugging in the exact same values into our compound angle formula, which lets us actually work with less difficult numbers. With that in mind, we can now move on. So, I hope you enjoyed the demonstration, and now I've simply written down all of the formulas we have derived. So, again, sine of 2x is equals to 2 times sine x times cos x. Cos of 2x has 3 different variations. The first one being cos squared x minus sine squared x. The second one is 2 cos squared x minus 1. And the last one is 1 minus 2 sine squared x. Now, for our tan, we have tan 2 of x is equals to 2 tan x minus 1 minus, tan 2x is equals to 2 tan x divided by, not minus, 1 minus tan squared x. These double angle formulas can help you prove some trigonometric identities a lot faster, as you won't have to apply the compound angle formulas anymore. You won't have to think about, what does 2x mean? What does 4x mean? It means you're adding theta 4 separate times, and so again, you're going to have to apply the compound angle formula, and it's going to get a lot more complicated than it has to be. So with that out the way, sorry, I had to yawn. We can now talk about the strategies for proving trigonometric identities. As with everything in mathematics, you can use several strategies to make your life a whole lot easier. Trigonometric identities might seem intimidating, with some of them being extremely long equations, but with these tips, you could prove them with relative ease. Again, it's relative ease because it's still going to take you a lot of time. So, the most important thing I could tell you is to always start working with the most difficult side. So this side, for example, could be the one that has the most parts to it. So you have like tan plus sine plus cos of x is equals to one single expression. Or that side might be something you haven't encountered before. So for example, I wrote in here sine of x plus sine of 4x. We haven't learned how to do that. So that might be the most difficult side you have to work with. Once you found the most difficult side, you could now apply our quotient identity, which is the one that says tan of x is equals to sine of x divided by cos of x. The reason why this is important is because if you're not dealing with solely tan, and you have a sine or a cosine within the function somewhere, or the equation somewhere, that would probably mean you have to perform this conversion. Otherwise, you're not going to be finding those groups of variables that you need to combine. Next, you should always try to apply any formula that you think might work. The reason for that is, if it actually works for the equation you're given, then you're most likely on the right track. Usually teachers are not going to try to confuse you for different identities or for different formulas that might work for the same exact problem. Lastly, I would say that you should clearly label the left and right side of the equation. So that could be just saying left side, right side, or how I like to do it is say 1 and 2. Because I personally find it much faster to just write 1 and then 2 rather than right side or r dot s dot, you know. That will help you organize your work a lot better, so you could actually understand the steps you're doing more properly or more in detail. That was English. And also it'll help your teacher understand your work. So even if you did make a mistake, you could clearly point out where it happened, and maybe you won't lose that many marks. Lastly, this is just a small little detail, but again, it'll just save you time in the therefore statement. As I said, I feel like writing 1 and 2 is much easier than right side, left side. Of course, as with everything, you have to practice solving these trigonometric identities. You won't get anywhere if you just memorize these formulas and not practice how to apply them. For example, some of these are extremely long. You need to practice writing them out. If you just remember them or like poorly remember them and then take another 10 minutes trying to jot down what the formula actually is, you're gonna waste all of your time. We had a thinking assignment where we were given 4 separate, I think, trigonometric identities in like the span of half an hour, and some of them will take you a full 10 minutes to solve just because of how many steps you have to follow or how long they get. So you can't afford to waste time trying to remember the formulas because you couldn't bother to write them down before. Now I've provided these 3 examples on how to several trigonometric identities. I tried to make them in terms of difficulty. For example, the last one was actually on our thinking assignment. There was one really fun one because it would take me a full page to solve, but I didn't put it here because I feel like, again, it's a thinking assignment question, and so you should already have practice with trigonometric identities before you dwell deeper into what the actual difficult ones are. So again, I'll be showing you how to solve these in a moment. Okay, so let's get started on these examples. So our first example is where it says that tan of 2x minus 2 tan of 2x sine squared of x is equals to sine of 2x. Okay, so we could easily identify which side is more difficult. Let's try and identify that side. Well, I would personally say that our first side over here should be the more difficult one, so I labeled it 1. Now let's work on 1. So again, since we have a sine in here, I'm going to rewrite tan as sine of 2x over cos of 2x. Now, same thing goes for here. Sine minus 2 tan sine of 2x, divided by cos of 2x times sine of 2x, sine squared of x. This is the same as writing out sine of 2x cos of 2x. Now we take this out, and what we're left with is 1, because we divided this by sine of 2x, and then minus 2 sine of 2x. What do we know this as? Well, we know that that is equals to cos of 2x, right? That's the other form that we have learned. So cos of 2x. Now we have the same denominator as our numerator, so we could cancel them out, and we're left with sine of 2x. As you could see, our first side is equals to our second side, so we could say 1 is equals to 2. We have proven our first example. Now let's go on to our second one. So what we have is cos to the power of 4 of x minus sine to the power of 4 of x is equals to cos 2 of x. This may seem a little bit suspicious. We have actually dealt with cos of 2x. We've derived what that is, but now we have a different value on this side. So let's see if that is true. Let's try to reduce this to that. Well, how can we do that? Let's think. At first, let's work with 1 again, because that is the portion that is difficult. So 1, we have cos 4 of x minus sine to the power 4 of x. I know I don't say it properly most of the time, but let's look at this format. We have something to the power 4 times something to the power 4. You might remember this is the same as the difference of squares. So like y squared minus x squared, right? Is equals to y minus x, y plus x. So let's apply that to here. So we have cos squared of x minus sine squared of x times cos squared of x plus sine squared of x. Well, what do we know from here? We know that cos squared of x plus sine squared of x is equals to 1. So we actually have cos squared of x minus sine squared of x on this side, right? We've also known for our second side that cos 2 of x is equals to cos squared of x minus sine squared of x. So we could actually just write down that this is equals to cos 2 of x. And again, we could now say that 1 is equals to 2. So we have proven the identity once again. Now let's do our third one. Third one, as I said, is a thinking question that I've received in my school. So, sorry, I keep losing the cursor. There you go. Found it. Our identity is the following. Sine 4 of x divided by 1 minus cos 4 of x times 1 minus cos squared of x over cos 2 of x is equals to tan of x. This seems a lot more difficult than the ones we've done before, right? What is our biggest problem here? Well, we're dealing with big numbers. However, we also have a tan in an equation that's talking about all of x's, or sines and cosines. So again, this seems like a more difficult part, this seems like a more easier part. Also, we could safely assume that this is supposed to convert into sine of x over cos of x. So let's try to do that. Okay, so let's work on side 1. First, I would try to cross multiply them. So I'd have sine 4 of x times 1 minus cos of 2x divided by 1 minus cos 4 of x times cos 2 of x. Right? That's what we get. From here, I would actually try to expand as much as possible. So each of the double angles, let's expand them. So sine of 4x, right, that is the same as a double angle formula for 2x, which would mean that we actually get 2 sine of 2x cos of 2x. This over here, we could actually expand further. So cos of 2x we know is cos squared of x minus sine squared of x. However, since we had a negative in front of it, this has to be a positive. Now let's do the same thing for the denominator. So 1 minus cos 4 of x is the same as, again, applying the double angle formula for 2x, so that's cos squared of 2x plus sine squared of 2x. And then over here we get cos of 2x squared is the same as cos of 2x minus sine squared of x. Now let's continue to expand because we still have angles left. So at first over here I will expand it to 2 times 2 sine of x cos of x times cos squared of x minus sine squared of x. And then again, let's expand it we have over here 1 minus cos squared of x plus sine squared of x. We know that 1 is actually equals to cos squared of x plus sine squared of x. So I'm substituting that in, minus cos squared of x. Need to keep expanding this. See, this is what I'm talking about. Like, you will be using all of the space you're given. Now, let's go for the denominator once more. We have 1 minus cos squared of x. That we could rewrite as our other form of the double angle formula for cos. So that would be 1 minus 1 minus sine squared of 2x plus sine squared of 2x. And then this stays the same. Cos of 2x minus sine squared of 2x. Okay, so now we could simplify a little bit. First of all, we see that these two are the same, so we could cancel them out. From here, we know this, we could multiply this by 2. And from here, we know that these two cancel out. From here, we know that these two would cancel out, and this would become a positive. So let's write all of that down. First, we have 4 sine of x cos of x times our remaining two variables, which actually add up to sine squared of x. Now, in our denominator, what we have is we had a negative sine squared of 2x. This became a positive, so we have 2 sine squared of 2x in our denominator. From here, you might get a little bit confused, but the easiest thing for us to do would actually be to multiply everything we have at the top, right? So what we would get is 8 sine to the power 3 of x cos of x divided by this over here. What does this over here actually simplify to? Well, as you can see, we have a square. So personally, what I'd like to write it as is sine of 2x times sine of 2x. This would in turn actually expand, as we know what sine of 2x actually is. So let's write the numerator once more of cos of x divided by 2 times 2 sine x cos x, and then again 2 sine x cos x. Make sure that line always crosses the denominator fully. Now let's actually distribute everything. So we would get 8 sine to the power 3 of x cos of x divided by 2 times 2 times 2 is 8. Then we have sine x times sine x, that's sine squared of x. And then we have cos x times cos x, that's cos squared of x. So from here, the 8's cancel out, the 3 and the 2 cancel out, leaving 1 at the top. This removes it, and this becomes 1. So what we're left with is sine of x over cos of x, which is equals to tan of x. That was our second side. Therefore, we have proven that side 1 is equals to side 2. With that out the way, we have officially finished chapter 4. This is the homework that I assigned for the last chapter. It is these questions of 7, 8, 9, 11, 15, 16, 17, and 18. The only thing is, I'm pretty sure I messed up the page number. The page number is supposed to be 240. So let's change that. There you go. With that, next class we'll be moving on to chapter 5, which is still dealing with trigonometric functions, but now it's less about solving equations, but more about graphing. So if that's your cup of tea, I hope you're excited. Personally, this was my favorite chapter so far, just because of how beautiful these solutions are. I love trigonometry, and like trigonometric identities are my favorite part of it. So if you have any questions on trig identities, please reach out to me. I'd be more than happy to help. But again, if you have any other questions, I would love to help you also. I hope you have learned a lot today, and I can't wait to see you next time. Bye bye!